Now the first example that we will look at will check what will happen when we add a small float like 1.0 to a medium and a large float. So first I'm declaring a variable called big underscore float. It is initialized with value equal to 100 million. The next one is medium underscore float. It's initialized with value equal to 1000. The last one is a little float and it's initialized with value equal to 1.0. So the question is what will happen when we add 1.0 to 1000 and 1.0 to 100 million. We know the result is 1000 plus 1 is 1001 and 100 million plus 1 is 100 million 1. But let's see what will be printed when we do this arithmetic with 32-bit single precision floats. Notice 1000 plus 1 is still 1001, but 100 million plus 1 is still 100 million. So what this means is 100 million 1 cannot be represented accurately using a 32-bit float. 100 million has more than 7 significant digits, and it's also greater than 2 to the power of 24. So we know that not all numbers beyond 2 to the power of 24 can be exactly represented using a 32-bit floating point number. Now the question is, what happens when we add 4 to 100 million or 5 to 100 million? Can these numbers be represented in 32-bit floats? So let's continue the execution and let's see what happens when we add 4 to 100 million and 5 to 100 million. So 100 million plus 4 is still 100 million. 100 million plus 5 is 100 million 8. So what this means is the next number after 100 million that can be represented using a 32-bit single precision float is 100 million 8. And all the numbers in between are only a closest approximation. So the closest approximation to 100 million 5 is 100 million 8. And the closest approximation to 100 million 4 or 100 million 1 is 100 million. So again, now let's verify what happens when we switch from floats to double. That is, now I've declared a variable called big underscore double, initialized to 100 million, and I've initialized a little underscore double with value equal to 1.0. Now let's add these two numbers and let's see the result. Now notice 100 million plus 1 as doubles is equal to 100 million 1. So when we switch from 32-bit floats to double, we can accurately represent the numbers that are greater than 2 to the power of 24. However, we will encounter the same issue as before with single precision floats, but only at a higher exponent. So if we now change the value of big underscore double from 1 into 10 to the power of 8 to 1 into 10 to the power of 16, we will again come back to the same issue. So let's continue executing the code. Now look at the result. 1 into 10 to the power of 6 plus 1 is still equal to 1 into 10 to the power of 6. So not all integers and floating point numbers can be represented when the numbers are large for both 32 and 64-bit floating point numbers. But it is seldom we will be operating with values like 1 into 10 to the power of 16. And if we actually want to do arithmetic at such high values with low floating point numbers, there are other techniques to avoid these issues. But we will not be covering them right now. So let's look at the next scenario. In the next scenario, we're checking whether a subtraction of two numbers is equal to the result that we expect. So here we are subtracting 8 minus 6. We know the result is equal to 2. And let's print both x is equal to 2.0f and the result of this operation where I'm subtracting 8 and 6. So we will print both as with 32-bit precision and let's see what will be the output. Okay, now notice both of them, x is equal to 2.0 and all the 32 bits are zeros, and x underscore clone is also 2.0. So we can accurately represent both x and x clone. That is great. Now let's look at the second example where x is equal to 0.25f and x underscore wannabe is equal to 0.75f minus 0.5f. So we know 0.75 minus 0.5 is equal to 0.25, but when we print it with 16 or 32-bit precision, let's see what will be the difference, if there is any difference between x and x underscore wannabe. So let's continue execution. And now we will see that x is equal to 0.25 with all zeros in the rest of the digits, and x underscore wannabe is still 0.25 with all zeros in the rest of the significant digits. So again, we can accurately represent 0.25 and 0.25 with 32-bit single precision floats. Now the third example is we're subtracting 0.8 with 0.6. So 0.8 minus 0.6 is 0.2 and x is initialized to 0.2. So now let's print out x and x underscore wannabe, and let's check with 16 or 32-bit precision what will be the values in x and x underscore wannabe. Now notice x is itself not equal to 0.2. So x is accurate up to 7 decimal digits, and beyond 7 decimal digits we have an approximation. So we have 029802322, and x underscore wannabe is not even equal to 0.2, so it is 0.1999999. So up to 7 decimal digits it's 999, and beyond that we have other decimal digits. So with 32-bit precision we are printing all the digits, and notice again it's only accurate up to 7 decimal digits. So now, based on what we looked at before we could do comparisons like x is equal to x underscore clone, we will get a true. We also can check x is equal to x underscore wannabe. When it is 0.25, we will get the result to be true. However, in the last case, it fails. Now, the reason why it succeeded in the first two cases was because the only numbers that can be exactly represented using 32-bit single precision floats are powers of 2's. So here notice it is 2 to the power of 1. In the second case, it is 2 to the power of minus 2. So only powers of 2 can be exactly represented using 32-bit floats, and non-powers of 2 are only closest approximations. So the third case, 0.2 is not a power of 2, and therefore it cannot be exactly represented with the 32-bit single precision float. So now, if we actually write an if condition which is checking whether x is equal to x underscore wannabe, this should fail. So let's continue the execution and let's see what is the output. Notice the if condition failed and the printers don't use equal to compare two floats. So if you want to compare two floats, you need to take the difference and check whether the difference is greater than some threshold, and never use equal to compare two floats. Next, let's look at what happens when we add three numbers. We want to check associativity. So we're declaring three floating point numbers here, A, B, and C. A is 100 million, B is 1.83 times 10 to the power of 5, and C is 50. So now first let's add A plus B, and to the result let's add C. And in the second case we will add first B plus C, and to the result we will add A. And let's print the result of both of these operations, and let's check whether they are equal. Okay, now notice again they're not equal. The difference is 8.0 f, which means that even though we know that real numbers are associative, we cannot make such assumptions when we are working with 32-bit floats in C++. So for some numbers, the associative property can hold. When we are dealing with very small numbers or when we are dealing with powers of 2, we know that we can exactly represent the numbers, so they can be associative, but it's not necessarily true always. Now the next example shows us what happens when we print a number which is greater than, which has more than 7 significant digits. So here I'm printing first 0.123456789 as a 32-bit float. When we suffix a floating point number with f, it's a 32-bit float. If the f is missing, it's assumed as a 64-bit double. So here, when we are printing this number as a 32-bit float, let's see what will be the output. And then we are printing a bigger number, so it's repeated again. So it's 0.123456789 followed by 0.123456789. So let's see what happens when we print these two numbers. Okay, now notice it is only accurate up to 7 significant digits. So we are seeing 0.1234567 followed by all the other digits are not accurate. Similarly, when we are printing the bigger number, it's only accurate up to 7 significant digits, 0.1234567. Beyond that, it is not accurate. It does not represent exactly what we are trying to print. So this again tells you that the number of significant digits with the 32-bit single precision float is only 7. If you want to represent accurately more significant digits, you need to switch to double. So now let's print these two values as double and let's look at the output. We know that double is accurate up to 16 to 17 significant digits. So now let's look at it. Notice the first number 1.1234567 and the remaining digits are now 88999999. So up to 16 to 17 significant digits we are accurate. And the next one, which is 0.123456789, 0.1234567. So again up to 16 to 17 significant digits we are exactly equal to what we were trying to print, and beyond that it is an approximation. So up to now we saw two things. One, not all floating point numbers beyond 2 to the power of 24 can be exactly represented using a 32-bit single precision float. And second, 32-bit single precision float only has 7-digit accuracy. If we want to represent bigger numbers or if we want more accuracy, we need to use double precision floats. However, double precision floats also has the same problem, only at higher exponents, and after 18 digits we will not have accurate representation of numbers. Now let's look at the